So in the linear algebra problem, I'm not stating things in terms of matrices and vectors at first, but the idea is that you can relate these things to matrices and vectors. You've got really two equations that define y1 and y2 as functions, if you will, of x1, x2, and x3, and three equations that define z1, z2, and z3 as functions of y1 and y2. The goal is to use matrix multiplication to determine how z1, z2, and z3 depend on x1, x2, and x3. I'm effectively composing these transformations. You could do this without matrix multiplication. How? By taking each of these y1s in terms of taking the y1 equation in terms of x1, x2, and x3 and substituting in these spots. And then taking the equation for y2 in terms of x1, x2, and x3 and substituting in these spots. So this could be done without matrix multiplication. But we also can do it with matrix multiplication, and that's the goal. And then we want to answer these questions. Is this composite linear transformation? I'm really composing two functions, two linear transformations. One-to-one, is it onto? Okay, let's define some vectors here. So the vector x, here it's good to use vector notation, little half arrow here, is going to be x1, x2, x3. The vector y has evidently just two components, y1 and y2. And then z is back to three components. So x is a vector living in R3. Anybody ever read Flatland? Okay, one person. It's about two-dimensional creatures, okay? And they can't imagine three dimensions. And these creatures are like circles and squares and triangles. They even made a movie out of it. This one lives in R2. This one is an element of R3. Three-dimensional vector, two-dimensional vector, three-dimensional vector. Okay, focus first on how y depends on x1, x2, and x3. I'm going to write it in vector form here first. y1, y2. Vector y equals y1, y2. Go ahead and replace y1 and y2 with how they depend on x1, x2, and x3. You didn't have to do this, but I'm trying to make a conceptual point here. And I do this in the lectures, that you can break this apart, this vector apart, into a linear combination of vectors like this to help you realize, hey, that's a linear combination of vectors. I could think of that as a matrix times a vector. What matrix? A matrix whose columns are these three vectors here: 1, 2, 2, -1, -5, 1. A 2x3 matrix, 2 rows and 3 columns, times a three-dimensional vector x1, x2, x3. I'll call this the matrix B times the vector x. So this thing here is the B. B is a 2x3 matrix. Question? Is there a 3? Oh, did I write it wrong? Okay. All right, thank you. So I wrote the wrong thing up here originally. There's a 3 here. Making a 3 here, a 3 here, and a 3 there. Thanks. So there's one of the matrices you need to multiply. What's the other matrix? Z is Z1, Z2, Z3. How does that depend on y1 and y2? Z1 is y1 plus y2. Z2 is y1 minus y2. Z3 is 2y1 plus 3y2. Split that apart into a linear combination of three-dimensional vectors. And you can write it like this. Being a linear combination like that, that can be represented as a matrix times a vector. This is a 3x2 matrix times a two-dimensional vector y1, y2. By definition of matrix times a vector, that you get this linear combination of the columns with the entries of the vector as the weights. I'll call the matrix A here. So this thing here is A. So in vector form, Z depends on X in the following way. Z equals A times Y, but Y equals B times X. And the associative property works here, though that takes proof. This is really A times B times X. So the matrix A times B, if you use this notation, is supposed to be the matrix you compute, the matrix product you compute to find the equation for this linear transformation. A is 3x2. 3 rows, 2 columns. B is 2x3. 2 rows, 3 columns. X is 3-dimensional. You could think of that as a 3x1 matrix. Column vectors can be thought of as matrices. When you multiply 2 matrices, the inner numbers have to match. These match. The number of columns of the matrix on the left has to match the number of rows of the matrix on the right. And the final answer is going to have dimensions equal to the outer numbers, 3x3. You should have gotten a 3x3 matrix. That makes sense. Z has 3 components and X has 3 components. It's going to have to be a 3x3 matrix. What I'm about to show you is the shortcut way to find the product, not the definition. The definition of the product says create a 3x3 matrix, the first column of which is this matrix times the first column of B. A times the first column of B. The second column is A times the second column of B. The third column is A times the third column of B, according to what it means to multiply a matrix times a vector. That's the definition of A times B. But practically speaking, it's not the most efficient way to compute it. A more efficient way to compute it is to use dot products of rows on the left with columns on the right. The upper left entry of the answer is the dot product of this row with this column, the first row and the first column. Pretending those are just vectors that you're taking the dot product of. 1 times 1 plus 1 times 2. 3. Right? 1 plus 2. 1 times 1 plus 1 times 2. The entry in the first row, second column, is the dot product of this row vector of the matrix on the left with the second column of the matrix on the right. So that's 1 times 2 plus 1 times -1. 2 minus 1 is 1. 1 times 2 plus 1 times -1 is what that comes from. I'm dot producting. I never said that before, dot producting. Dot producting this row, the first row of the matrix on the left with this column, the second column of the matrix on the right. This is the shortcut method for multiplying matrices, not the definition. For the third row, or first row's third column, stay with the first row of the matrix on the left, go to the third column of the matrix on the right. Do the dot product, 1 times -5 plus 1 times 3, -2. That's 1 times -5 plus 1 times 3. Now we're on to the second row of the answer. Second row, first column, what goes right there? It would be the dot product of the second row with the first column. Second row, the matrix on the left with the first column of the matrix on the right. 1 times 1 plus -1 times 2. is 1 minus 2 is negative 1. For this entry in the second row, second column, dot product of second row with second column. 1 times 2 plus negative 1 times negative 1. 2 plus 1 is 3. For the second row, third column, do the dot product of the second row with the third column. 1 times negative 5 plus negative 1 times 3. Negative 5 minus 3 is negative 8. Finally, for the last row of the answer, A times B, use the last row of the matrix on the left. Dot producting with the columns. 2 times 1 plus 3 times 2 is 2 plus 6 is 8. 2 times 2 plus 3 times negative 1 is 4 minus 3 is 1. And then 2 times negative 5 is negative 10 plus 3 times 3, 9. Negative 10 plus 9 is negative 1. That gets multiplied by x1, x2, x3. And if you do that and simplify, in the end, you get a vector 3x1 plus x2 plus or minus 2x3. Negative x1 plus 3x2 minus 8x3. And then 8x1 plus x2 minus x3. Did anybody get that far to say that it looks good? Okay. So this is a mechanical process for composing two linear transformations. Multiply their matrices. It turns out this works. You would get the same answer here if we did that substitution stuff I mentioned at the beginning. The substitution would be technically faster. But with bigger matrices and computer technology, it's better to think in terms of matrix multiplication. What about whether this is one-to-one or onto? Typically, for a linear transformation from R3 to R3, defined by a 3 by 3 matrix, typically it's going to be both one-to-one and onto. However, in this case, it's not. You can use row operations to confirm it, but intuitively, why is that the case? Intuitively, think about, first of all, this transformation from x to y. If you think of it as a linear transformation, let's use the letter T. From 3-dimensional space to 2-dimensional space is going from a higher dimensional space to a lower dimensional space. Some sort of collapsing is going on, you might imagine. Vectors in 3 dimensions are getting mapped to vectors in the plane. Should be somewhat intuitive because of that many vectors will get mapped to the same thing. And in particular, many vectors will get mapped to the 0 vector. The kernel of this is going to be non-trivial. If you did row operations with B, trying to solve a system of equations where the right-hand sides were 0, imagine an augmented matrix, you couldn't get a pivot in every column of B. At least one of these columns, typically the third column, would not have a leading 1. And that's going to mean there's free variables. And if there's free variables, there's going to be more than one solution, because the free variables can be anything. So T is a linear transformation from R3 to R2. It can't possibly be one-to-one. Is it onto? It does turn out to be onto. These column vectors don't point in the same direction. They're not parallel. They're going to span the entire plane, so to speak. Linear combinations of these will give you any vector in the plane. I hope that's somewhat intuitive if you draw those 2-dimensional vectors in the plane. They're not pointing in the same direction. If you take linear combinations of them and think geometrically in terms of vector addition, you will get every possible vector in the plane. The other transformation, defined by A times Y, call the transformation S, takes a 2-dimensional vector and gives you a 3-dimensional vector out. T is defined by B times X, S is defined by A times Y. When we multiply the matrices, we're really doing the composite transformation. Z ultimately equals, well, at first it equals A times Y, which is S of Y. But Y is T of X. So Z is S of T of X. Using circle notation for function composition, you could write that like this. S compose T of X. S goes from a lower dimensional space to a higher dimensional space. Does that mean somehow it does expand the two-dimensional plane into three-dimensional space in some weird way? No, it doesn't. Linear transformations can't act that wildly. Some nonlinear functions can act that wildly, but not linear functions. Linear functions are very tame. It not going to take a two-dimensional plane and somehow morph it into a three-dimensional space. It's going to map it to a two-dimensional plane, most likely inside three-dimensional space. Not necessarily the XY plane, some slanted plane through the origin, because the zero vector gets mapped to itself. It's not going to be onto. When you compose them, ultimately in this composition, you're going from R3 first to R2, then to R3. You're collapsing, so the result can't be one-to-one. And then you're expanding, so the final result can't be onto. It's going to be neither. That can be confirmed with row operations. Let's just double check that. In Mathematica, the way to do row operations most nicely and also have your answer look like a matrix is to do matrix form, row reduce. I'm going to type the matrix in here. So I just clicked the matrix button over here on the palette. To add an extra column, do control comma. Comma starts with C, just like column starts with C. To add an extra row, do control return. Return starts with R, just like row starts with R. I could add another column for my right-hand side numbers, but when we row reduce this, we'll see that we do not get a pivot in every row or every column. We get a row of zeros, so there's not a pivot in every row. We don't get a column of zeros, but we do get a column that doesn't have a leading one in that given row. If I imagine zeros on the right-hand sides of an augmented matrix, the resulting homogeneous system would have infinitely many solutions because Z would be a free variable. X would be -1/5 times Z. Y would be +13/5 times Z, and Z would be itself. But the kernel would be non-trivial. Plenty of vectors, infinitely many, get mapped to the zero vector. As far as showing it's not onto, what you'd really want to do is you'd really want to imagine an arbitrary numbers over here on the augmented matrix A, B, and C. And effectively what you would end up with when you do row reduction by hand is in that augmented matrix in the lower right corner, you would actually not get a zero. You get something involving A, B, and C. And unless that thing involving A, B, and Z is zero, the resulting final equation from the final line would be inconsistent. Zero equaling something non-zero. And therefore, that would mean it can't be onto. A, B, and C could not be anything. They would have to satisfy some expression involving A, B, and C equaling zero. Let me go ahead and try to see if I can add another column here. No, that didn't work. Well, I guess I can do this one by one, adding. Let's try this with an arbitrary A, B, and C there. It's not working. Okay. Oh, I think that's because Mathematica doesn't know what I'm doing. Hang with me. Let's try to redo that. This is worth doing. Okay, so the original matrix again, 3, 1, -2. Let's put an A here. -1, 3, -8. B, 8, 1, -1. C, I'm trying to solve an arbitrary system. Okay, actually, it's not something involving A, B, and C over here. With Mathematica, it's giving me a 1, saying 0 equals 1. I think Mathematica is assuming A, B, and C are such that you would not get a solution. Actually, if you did it by hand, you would get an expression involving A, B, and C here if you did it by hand. So Mathematica is not being quite as ideal here. some expression involving A, B, and C. If that expression equals 0, then that is a possible output. But if it's not, which is going to be typical, you're not going to get a solution. So it's going to be an inconsistent system. So the transformation is not going to be onto. Can't just leave here hearing me say those things and imagine you could be able to answer that kind of question on the test, just listening to what I just said just now. You got to rethink about stuff, okay? Otherwise, it's in one ear and out the other, and it's not going to stick in your brain. So think about these things. Go beyond the ordinary homework. Try the supplemental problems, the optional problems. Try rethinking about things from the lecture. Okay? Have a good day.